So welcome to Elec207 Control Theory Lecture 10 Control System Design. We are going to design some components using the loop cool root. So from process, this is let's talk about the design while root locus. Okay. So before we're going to do that, we're going to introduce some components called compensators. So there are going to be two kinds of compensators. The first one is called cascade compensators, and the second one is called the first one is called cascade compensator. The second one is feedback compensators. We are going to focus on the cascade compensators, which is just this is the compensator, this is the general GS, and this is the PS, which is the planet. The planet is controlled by the GS, but we are going to have a compensator before the GS. So let's look at the cascade compensator. So for the cascade compensators, we have the GCS as the input. So it's a cascade, means they are cascaded linked, and for the feedback compensator, it's just like we put the compensator in the feedback loop, but here we put it in a forward loop, okay, forward path. And the compensators are just something like why do we need compensators? The compensator is just like we would like to improve the steady state error. So what is steady state error? The steady state error just means that what if the system is eventually going to reach some state, right? So, but the actual state might be like here, okay? So therefore, what if it is so after we reach a steady state, the difference from the the real one and the expected one is the steady state error. So there are two types of system, which is the system type 1, system type 0, and system type 2. So what are the difference here? The difference here is just like so what if we look at the transaction function of the GS? What if on S approach to 0, how many S minus 0 in the denominator? What if there is 1, then it is type 1. What if there is 2, then it is type 2. What if there isn't 1, it is type 0. So we only care about 3 streets. So why do we care about that? Because once we have one of the S divided minus 0, then we have one divided by S. Remember, what is the 1 divided by S here? The 1 divided by S is an integral. So the integral, what if we integral of some error, then it is something dramatically different. Therefore, we care about the S minus 0 in the denominator to determine whether it is system type 1, type 0, system 2. Okay. So let's look at the input. Okay, the input we differentiate into 3 types, which is step, ramp, and parabola. The input 1, what is unit step, which is x equals to ut, and for ramp, x equals to t. For the parabola, x equals to t squared divided by 2. So it is worth noticing that what if it's type 1. Okay, so for the input is where the system we can handle, right? There is a system we can handle, and for the system type 1 that it can handle, right? It definitely can handle. So just like we are matching, okay? And for this, what if the input is ramp, but it goes to a system type 0, then the system may not handle it. And what if it's the input is unit step, but we come to step type 1, then the system say, okay, it's so easy, there's no error, okay? And for example, what if it's like a ramp and type 1, then it's like, okay, we are matching, okay? And for parabola, then for type 1 and 2, they're going to say, you cannot hold me, you will have infinite error. But for ramp and step, there's going for type 2, there's going to be no error. And for the parabola, we will have corresponding matching error, so which is 1 divided by k. So let's look at the lag compensator. So system type. So unity negative feedback representation of the system. So for in this case, it's going to be 2, 2 system type 2, and let's say the PI control integral compensation. So Kp plus Ki divided by S equals to Kp times S plus Ki divided by Kp divided by S. So the thing is just like what if the Kp is uncompensated? What if the Kp is uncompensated? Then it is going to have this should be 2 holes, right? This system should have where is the J is going to be. So the first thing here is that what if we introduce the PI control? Then this is the transfer function of the PI control, right? What if we get the PI out, Kp out, we will have one additional additional 0 and additional hole. And the thing is that what is this one? Why do we conclude the compensator error? Look at that. So this is 201 class content discussion board control. Why do we draw the uncompensated Lucas root like that? Uncompensated. Lucas root like that. What? What is the corresponding function? Is it 1 square s minus 3 s square s 方加上乘以 s 减3乘以 s 减4乘以 s 减5乘以 s 括号里 s 减4乘以括号里s 减4，然后再乘一个 s 减5，乘一个 s 减3。s 减3， 记得不是加了吗？ So this is the thing I do not understand. Let's look at something new. Okay, let's do something new. So after that, we would like to see that that it's going to be very interesting course. Okay, that's really interesting. So what that will look like? So the thing is, so the improving the steady state error, we have the integral ideal integration compensation, the uncompensated with the pole at s equal 0, pi uncompensated, and so let's assume that is fine, okay? And with the pole at s equals to 0, which means there's going to be 4 poles, so it's going to be a 4. It is dramatically change the shape of that. What is pi compensated? We are going to add a pole and 0 at the same time, so it's great. So nothing changed, okay? So and what if we improve the steady state error? Then we are like, what we would like to say is just like what if the we are improving the steady state error because we are actually shifting the type from left to right, which means that we are going to have a stronger system to hold any of these things. That is feedback. Okay, that is compensator. And so how does the lag compensator comes into play? We can consider an example for a ramp input of type 1, okay, system. And for example, let's assume this is correct. So this is the limit t equals to infinity et is going to be the limit error. So the error when t approach to infinity is going to be 1 divided by kv, and kv is going to be the limit of t approach to 0 s times gs, and the poles kv is equal to limit s equals to 0 s times gs times s minus zc divided by z minus pc, which is going to be kv times zc divided by pc. The lag compensators only require positive components, resistors and capacitors, where pi components requires active components, operational amplifiers. So that is the thing, that the cascade compensators, they are just the improving the transient response. Dominant poles are the poles that are 5 times closer to the imaginary axis than others. And we can appropriate the transient response by considering the first order or the second order system defined by the closest poles to the imaginary axis. And for example, that's improving the transient response. The dominant poles are the poles that 5 times closer to the imaginary axis than others. We can appropriate the transient response by considering the first order or second order system by defining the closest poles to the imaginary axis. So the PD control, the ideal derivative compensation, the uncompensated is here, the compensated is great. So the PD compensated, and adding the PD control is going to alter the steady state error. So improving the transient response, the dominant poles are the poles that are 5 times closer to the imaginary. So in general, they are going to be less than 1 or going to be 1 or 2 dominant poles, right? So in this case, these 2, okay, are the dominant poles, and we can appropriate the transient response by consider the first order or second order system. So let's look at this. How is this look at? So in order to do that, we would like to download Mathematica. So the thing is, I do not have Mathematica, so that is a bad thing, right? Can I use that? I want Mathematica. Just try. Okay, I think it may not work that well, but I think maybe it is good. Let's look at Mathematica. WO哎。18就18吧。啊，这个就不要录了吧。这个